All right, class, we're gonna get started. Okay, so just a few announcements before we get started for today. And this has been revised from the version of the slides that I uploaded last night. So, but all this information, all the announcement information will be posted to the class syllabus. So first of all, lectures, I'm gonna switch where I put the lectures. I'm gonna put them on YouTube instead of Google Drive. It just, it helps me see actually where you're viewing the videos on YouTube. I can use YouTube Analytics to kind of see if there's something that's a particular sticking point as people are rewatching lectures. And so that's what I want to try this year. TA office hours are to be in the ICC starting next week. So not today, but next week, Monday, Tuesday, and Wednesday. Adriana is going to have hers on Monday and Wednesday from 5:30 to 6:30 p.m. So a little bit later in the day. And then Rob is going to have his on Tuesday 4 to 5 and Wednesday 1:30 to 2:30 p.m. Okay. So in addition to office hours, I met with the TAs yesterday, and they mentioned that Ed. How many people have used Ed as a class discussion? Yeah, many of you have. They mentioned that Ed has been very helpful to them in the past for course discussion, in particular for talking to the TAs, maybe when you can't make it to office hours. And so I set that up. It's my first time using Ed as a discussion platform. I see it's integrated into Canvas, but I'm expecting the TAs are going to help me make sure that we manage it properly for the class. But there's now a new link available on Canvas. If you look in the panel on the left-hand side of the Canvas page, that opens up the Ed course discussion. Other announcements, homework 1 will be assigned today. It's basically going to be a test, or not a test, but it's basically going to be a review of math. So there's going to be some derivatives, review of integrals, some separable differential equations, right? Simple differential equations, that kind of thing, that you'll have to solve. And again, just as a reminder, your submissions will be uploaded to Gradescope. Okay, and then today's lecture, we're continuing kind of our preliminaries, definitions and things in fluid mechanics. We're pretty much going to finish chapter 1 today by talking about these topics: dimensions and units, density, viscosity, and Newtonian fluids. We may get into the start of fluid statics, which is chapter 2 as well. But before I get started on that, any questions on anything from last time? Yeah. What do you mean? I mean, I guess I'm pretty particular about you uploading things to Gradescope. So, so for the homework, you will see that I will give you a template sheet with the homework where you should put your answer should fit into a box on the template sheet. And so it'll be labeled as where the answer goes. And then there will be room for you to work it out. But if that's not enough room, you can append additional pages. Does that make sense? Yeah, and that's because Gradescope is pretty particular about exactly where your answers are. And really, the main reason why I'm using Gradescope on the homeworks is that we'll be using it on the exams. And so on the exams, you're going to get sheets that look very much like the template sheets that I'll give you on the homeworks. And I want you to have practice using that before you get to the exam. Does that make sense? Yeah. Yeah. You can print them off and do the work. If you're working on a tablet, you can use template sheets on a tablet. That's fine as well. Yes, but it would be easiest if you print them off and then scan and upload. Yeah. Any other questions? I saw the hand. Yeah.
So the exams printed and given to us, and then we have to scan.
The exams will no, you do not have to scan. So on the exams, they will be printed and given to you. They're handed out in class, and then I'll collect them and I'll do the scanning myself. Okay. Yeah, because there's no time for that. I'm not gonna make you all run and stand in line at the scanner or something. Any other questions? Okay. And again, I use Gradescope because it makes it easier to grade fairly, right? I can grade one problem at a time and assign a rubric or set up a rubric so I'm giving everyone the same points for the same, answering the same piece of every problem. It just streamlines that process. In the past, like if I decide later on after grading the exam that, something that's, maybe 25% of the class had written on their exam and answer to problem 1A was actually correct, then I would have to remember which 25% of the class actually had that and go back and assign all the points manually. So Gradescope lets me do that all automatically. Okay, any other questions? Great. All right, so dimensions are going to be fundamental to a lot of the work that we do in this class. And dimensions are different than units, right? So dimensions are like the fundamental physical quantities that we are actually trying to measure when we use units. There are 4 primary dimensions that we're going to be using in fluid mechanics. And these are mass, length, time, and temperature. And you'll see we'll write these out as M, L, T, and theta. And then, and basically every variable, every property that we consider in fluid mechanics, we can write in terms of just these 4 primary dimensions. So for example, if we have a velocity, right? A velocity would be a length per time, right? And so we would consider this to be a secondary dimension, and we can write all of those in terms of these primary dimensions. Dimensions are not units. We use units to describe dimensions, right? We use units to describe, how long something is. But the concept of length is what we're getting at with dimensions, and that doesn't care about how long, some rod in France is, right? The historical definition of a meter, or how long some king's foot was, 1,000 years ago or whatever. So this becomes important. Like we're going to we're going to do dimensional analysis of equations in fluid mechanics. And from this, we're going to derive dimensionless numbers like the 2 that we've already been introduced to, right? The Reynolds number and the Knudsen number, by using this kind of information. So now to units, I should probably switch these 2 because this is what you're more familiar with, but we use units to describe or to measure quantities with those fundamental dimensions. And in this class, we're going to be using 2 unit systems. The SI system, System International or International System, and the British Gravitational System. So that means for mass, we have kilogram, or the slug is the BG unit. For length, meter, time, second, and temperature, Kelvin. So those are the primary unit systems that we'll use in class. You will encounter some other unit conversions on homeworks and exams. Another thing that I do like to do as a homework, at least, is give you a data sheet, like a manufacturer data sheet for a valve or a fitting or something, and ask you some questions about the equations presented on that data sheet. And when we're looking at data sheets, you're often going to see some really, really strange things. We'll hit on this again later in the lecture, but you'll often see some really strange kinds of units and dimensional conventions. So what this means, though, is that unit conversions will be part of this class, as they are unfortunately still part of life as an engineer, especially in the US, right? I'm sure you've seen this. I mean, in thermo, this is like a fact of life, right? But it's also a fact of life in fluids. You can buy actually our textbook inside units only. You might have seen that on Amazon. But we are using the version of the text where we have other units to consider as well. So when confronted with weird units out of SI or BG units or something you're familiar with, my suggestion is really first convert probably to SI. Honestly, that's how I solve a problem with units. Even if I'm presented with something in BG, I convert first to SI and then work out the problem, and then do a unit conversion at the end if asked for it in some other unit system. Yeah, that is my definite preferred strategy for solving problems. The conversion factors, so you have some conversion factors listed here. There are also conversion factors in a table in the back of your textbook. On an exam, if you're worried about that, I typically give that table to you as part of the part of some supplementary materials on the exam, reference materials on the exam. If there are any weird unit conversions that I'm throwing at you on the exam, it'll probably be on that table as well. I'll append it to that table. But yeah, this is my hint on units: convert to SI first. About dimensions. So when we're going to be looking at equations that describe mass, momentum, and energy balances in fluids, right? That's fundamentally what we're doing in this class. And any equation that we see must be dimensionally homogeneous, meaning that each additive term has the same dimensions. So for example, we will derive Bernoulli's equation, and we'll use Bernoulli's equation quite a bit. But if we look at this, dimensional homogeneity means that each term in this equation, meaning like here I'm calling a term, this 1/2 rho v squared is another term, rho gz, this is another term, even this constant is a term. Each term, right, each additive term in this equation must have the same dimensions. And so in this case, they are all expressed in dimensions of pressure, right? Everything written in dimensions of pressure. How do I know that it all has to be in dimensions of pressure? Because pressure is by itself, right? The pressure is by itself. So I know, even without doing, all the, analysis of, remembering that, okay, density is mass per cubic length and velocity is mass per length, and then square it and do all the simplification. Even before doing any of that, I see this pressure alone here. And I know that if this has dimensions of pressure, then this must have dimensions of pressure, or else there's something wrong, right? This must have dimensions of pressure, okay? Incidentally, have you ever been in a lecture where a professor raises their hand and says, excuse me, there's a problem with equation 6 on your slide or whatever? This happens occasionally at seminars, even at a conference or something. This can happen. A lot of times, this is the trick that person's using. They're looking at the expression and realizing, maybe I've dropped the 2 here, and it's just 1/2 rho v. And if I look at this expression and quickly do the unit or the dimensional analysis in my head and see that this is pressure and this is not the same units or same dimensions, then you would instantly know that there's a mistake here. That just can't be true. So units should be consistent among terms, meaning that if I express this in essentially pascals, say, then I should be using units here that also resolve to pascals. But that doesn't necessarily have to be true. So if we're working in SI or BG units, this will be true. Not necessarily true with all English unit systems, and definitely not necessarily true in all manufacturer data sheets. So this is a place where you'll often see some kind of weirdness. You'll see an expression here where they give this in pascals, but Z, height is measured in inches or something. And then there'll be some lookup factor that you multiply this term by. That's basically your unit conversion factor, but it's been baked into the data sheet somehow. So you will see this fairly often. Actually, one way you would maybe pascals and inches is maybe contrived, but you will see it in, for example, with PSI, right, pounds per square inch, and then Z measured in feet, right? That's something you might see on a data sheet. And then typically there'll be some prefactor, some multiplicative factor in front of one or more of these terms, maybe given in a table on the data sheet, depending on what units you're using. And that prefactor has basically all of that unit conversion built in. I'll see what I can come up with when we get to that homework, probably next week, for a manufacturer data sheet for you to look at. But this is, and the reason I hit on this so much is that this is something as a newly minted engineer, you may be tasked with understanding, right? You know, say your boss says, "Oh, here's a data sheet for some new piece of equipment we want you to size," or maybe just here's some new piece of equipment that we want you to size. And you go look up the manufacturer data sheet. It'll have a bunch of equations on it that are somewhat like the equations that we've learned in this class or that we've discussed in this class, but often in all kinds of crazy unit schemes based on just historically what industry it was used in. So this is definitely a very real world application of units and dimensions. Okay. So I want to do just a little exercise with you all. If you're paying attention, I gave you the answer to one of these already. But on dimensions, so I want you to get into groups of 2 or 3, and within your group, just discuss these 4 quantities of velocity, density, distance, and force, and just tell me what are the dimensions of these. Remember that we're going to be writing everything in terms of m, l, t, and theta. So as an example of what I'm looking for, acceleration, a, we would write as L t to the -2, meaning L per t squared, okay? So please get into your groups, couple of minutes, groups of 2 to 3 students, and please start discussing. Thanks.
It's fast. We have accelerated.
So what do you get for force? Got it. We're working on that. You discuss too as well. It'll help other people if you're not having trouble with it. What are you getting for force? Please work it out, and if you wouldn't mind discussing as well, thanks. All right, I think we'll call it there, even if you haven't gotten through all 4 examples yet. Okay. So in the sloth shirt in the back, you already spoke today, but yeah, what does it say? Not fast, but furious. Nice. What'd you get? What'd you get for? I don't know. Choose one. great. Okay. All right. Who has velocity? Sure, in the mask in the middle hand. LT to the -1, right? Length per time. Density. Who has density? Yeah. ML to the -3. Yeah, right. Mass per volume, right? L to the -3. All right, force. And for this one, I want you to describe how you got there. Yeah, in the middle. Yep, and acceleration was already making that a little bit easier for you. But yeah, that's exactly it. All right, so those are our dimensions. And if you're looking in the text, a lot of this and the answers to this are in table 1.2. So those of you following along on the slides may notice that this slide is not on there. Is not on the version that I put up on the Canvas site. But prior to the exams, I will upload rather a complete version of all the slides, including sort of the answers to these questions. So you don't have to furiously scribble all this down. And I will also include any corrections, right? So any mistakes that I make as this, I'll make corrections to those slides before I give you the complete version. Yeah, so this is also in table 1.2. So if you're confronted with some dimensional analysis, as you will be when we get to chapter 5, then this table 1.2 is really handy to look things up. And notice here, it also gives the units associated with these dimensions. Any question on dimensions or units? So this is a little bit strange, right? This idea, I mean, we're used to units, I think, right? By this time in your engineering career or engineering education. But this idea of dimensions is a little bit strange. But we'll see it has some power, which we'll really get to see in chapter 5 when we start doing dimensional analysis. But you've already got a hint of in terms of the non-dimensional quantities. So Reynolds number, if we wanted to write the, what are the dimensions of Reynolds number? Does anyone, what are the dimensions of Reynolds number? Dimensionless, and you'll sometimes it's written as 1. Or it has the dimensions of 1. So this notation here, this like curly brace, we use this to denote, like force has the dimensions of m l t to the -2. Sometimes you might see RE has the dimensions of 1, meaning it is dimensionless. And Reynolds number is, as I mentioned, a powerful tool for understanding or for getting an entry into what's going on in some kind of unknown flow. And we'll see that it governs a lot of the behaviors that we're going to describe in this class. And we derive it, and we'll actually show how we can derive it from the Stokes equations, but we derive it using a dimensional analysis. Okay, so another thing that we need to discuss before we can start answering problems with fluids are fluid properties. So one of the key fluids that we will be discussing in this class is density, or rho. And we're going to consider, actually, we're going to discuss density a little bit differently for liquids as well as gases. Remember, both liquids and gases are fluids. They both obey the conservation laws of fluid mechanics, or in mathematical terms, they both exhibit continuous deformation under shear. And so in a liquid, this density rho is approximately constant. Also a very weak function of temperature. And therefore, we're generally going to be assuming that liquids like water, oil, are incompressible, meaning as we apply pressure to a liquid, the density does not change. And we'll see that this will greatly simplify our equations of motion of a fluid. In a gas, rho can vary, right? The density can vary, right? Think about like the ideal gas law, right? We can relate pressure to density. Right, so ideal gas law will often apply. And therefore, we will sometimes treat gases as compressible, meaning we will other times be treating gases as incompressible, despite the fact that we all know, for example, the ideal gas law. So we'll develop this quite a bit further when we get to chapter 3. But there are cases where we can approximate the flow of a gas like air as incompressible, as with density constant. And the reason we do that is so that we can use the simplified forms of the fluid mechanics equations that apply to incompressible fluids. Okay. And then towards the end of the class, we'll get into what you have to do to treat gases as fully compressible. And we'll talk about compressible flow, and that's where we get into like aerodynamic shock waves and all kinds of other cool things, but complicated things. So the other major fluid property that we're going to be discussing is viscosity. And viscosity, we can think of as a measurement of a fluid's resistance to flow, right? Water is not very viscous, right? Water has a relatively low viscosity. When I say relatively low, like relative to something like honey, right? Honey has a high viscosity, has a high resistance to flow. And so if we were, should put those values on here, but if we look at the values of viscosity for honey and water, we'd see a large difference between the two. I'm just looking to see if I have it on the next slide. Of course not. But so we're going to put some math behind this, right? So let's to define what we actually mean by viscosity. We're going to consider that we have a fluid element that is deforming due to shear. So imagine we have some, little, in this case, square. Let's consider it to be sort of infinitely long, right? So it's a long, square-shaped thing, and we're now deforming it due to shear. So we're moving top face relative to the bottom face. So if I apply a continuous force, what happens? Does this thing stop moving or keep moving? What happens here? It keeps moving, right? Because that's the definition of a fluid. In a solid, right? If we had like a block of Jello here, we shear the top face, it would eventually stop moving, right? We would shear the whole block over, unless we tore it apart, right? But in a fluid, if we do this, if we apply constant thing, it's just going to continuously move. So we're going to consider this fluid element moving due to shear. At the bottom, we're going to say the velocity u is 0. At the top, we say it's some del u, right? Some small amount of velocity. And so for a fluid, deformation will continue as long as the shear now is applied. So for some fluids, the rate of shear, the rate at which we see this motion, the rate at which we see this block deform, will be proportional to the shear stress. Yep, go ahead. Yeah. Yeah. Yep. Yeah. Good question. That should have been explained on the previous slide. So the shear stress tau, this is a force per unit area. Yeah. So it is the force being applied at this upper surface per unit area of the fluid, per unit surface area of the fluid up here. Yeah. Yep. It is. So we will consider that in depth. Later in the class, but yes, it is. So if we'll consider at some point all the forces on a fluid acting on a fluid element, and we'll see that shear stress acts on these parallel to the surface, whereas pressure acts normal to a surface. Yeah. those of you asking what's going on right now, we will cover this in a lot more detail at a later point. So the shear stress. But for now, right, if you're not following with that, what I want you to think of as shear stress as just the force that we're applying to this fluid element in order to move one face relative to the other. Okay. Yep. Yeah, I mean, it could be. So let's say we have a bearing. So the question is, what are some examples of the type of force used to apply shear? So we could, for example, have a bearing where we have some oil in here, right? A film of oil between a shaft that's rotating and something that's held constant, right? If we zoomed in really, 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 really close, right? Or if we had this gap become really, really thin, then this looks like this same situation that's being applied here, right? Where we have a fixed bottom surface and an upper surface that's moving. And then the equations that we'll develop for shear stress or for this force and how it relates to the fluid properties would hold to figure out what is the velocity profile within this gap and what is the force required to turn the shaft inside of this bearing. Make sense? Any other questions here? Okay. For some fluids, the rate of shear is linearly proportional to the shear stress applied. So basically, the rate at which this angle changes is linearly proportional to the amount of force that we applied. So if we apply more force, or we apply double the force, we would get double the rate of change of this fluid element shape. So we can do some trigonometry on the angle there, theta, and note that the tangent of this small angle, d theta, is du, dt, dy, where, remember, u is the velocity, is the rate of change of displacement in x per unit time. So if we multiply this du by dt, then we get the dx, right? The distance that the block has sheared over in a given time. And then in the limit of small angles, this tangent of d theta just becomes d theta. And we can bring this dt over to this side and come with this expression that the derivative d theta dt is equal to du dy. Right, so rate of change of this angle as a function of time is equal to the rate of change of the velocity with distance y to move up this block. Yep. It's a good question. We are right now, we're considering the limit of small angles because we're going to use the expressions that we develop here. So essentially, we derived a differential equation describing the rate of change of the velocity with respect to y, right? And so, yeah, as far as a limit on small angles, I don't know, 1 degree or something, I guess would be what you would consider. But in this differential equation, remember when we write a differential equation, we're looking at, we typically derive this by looking at the limit of things getting really, really small, right? Shrinking all the way to 0. And so, this is valid as we shrink that angle all the way to 0. And now we have, so we have d theta dt is du dy. We previously said that for some fluids, tau is proportional to d theta dt. And so now we're going to use that. Yep. Yeah. So delta is the finite, for example, here, delta is like the finite size of some small little control volume. And then if we take the limit as that delta goes to 0, then we write it as a differential. So that makes, yeah, sorry about that. Yep. U is the velocity of the upper surface of this block. Okay. What else? Okay. So in the limit of small angles, right, these finite quantities become these differential quantities, right? So we really are truly considering things that are in the limit of approaching 0. And now we're really relating the rate of change of theta in time to the rate of change of velocity with distance y. Okay, so for this tau proportional to d theta dt, we can rewrite this as tau is equal to mu d theta dt, where mu is that constant of proportionality is our viscosity. And then if we plug that in here, we end up with tau is mu du dy. Sorry, the mu tau is d theta dt. And now we'll end up with tau is du dy. Mu du dy. So this relates the shear stress that's being applied to the velocity profile that we see across the or to the rate of change of velocity across this fluid element. So if we and we say that a fluid that follows this linear relationship where tau is mu du dy, we call that fluid a Newtonian fluid. So this is essentially our definition of what a Newtonian fluid is. So a Newtonian fluid is a fluid for which tau is mu du dy. Yeah. So this defines Newtonian fluid. That's correct. Yeah. And it comes from our initial assumption that, we said that for some fluids, the rate of shear is proportional to the shear stress that's applied, and that we can develop this relationship, which is our definition of a Newtonian fluid. Yep. Yeah, the initial statement is also a definition of Newtonian fluid. We typically write it out this way because we're not often considering angles, right? When we're we don't often consider angles when we're trying to figure out how fluid elements deform. Most of the time, we're more concerned with velocities, right? So this is generally what you'll see as the definition of Newtonian, but there we were assuming a Newtonian fluid without saying so. Yeah, that's right. Yep. Exactly. That mu is just a proportionality constant that we call viscosity. Okay. And we so earlier, basically, I said that viscosity we can think of as the quantity that measures a fluid's resistance to motion, right, to velocity. And this is really just putting that into math terms, right? Yes. 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 This is the definition of fluid viscosity for a Newtonian. Just mu, yeah. But this is where it comes from. This is what the role of viscosity is in a Newtonian fluid. I saw a few more hands. Yes. So something like oobleck is not a Newtonian fluid because it does not have a constant viscosity. That's correct. So we would call oobleck a non-Newtonian fluid, which is maybe on the last slide we're going to get to today, and in the videos we'll look at on Friday. Other questions? Yes. That's a good question. Is there? Does viscosity have units? Yeah, viscosity does have units. Yes, I mean, we will typically consider viscosity in SI, right? And so if we go back to our slide here, then we'll see, we can write in SI units, we'll have viscosity will have units of kilogram per second. You'll often sometimes see like poise or centipoise for as units for viscosity, sort of non-SI units for viscosity. But generally speaking, we're going to be talking about viscosity in SI units. Although on a data sheet, for example, we might see something strange. Yeah. Other questions? Yes. So we're concerned with, no, we are not only concerned with surface velocity. So we've ended up with a differential equation that describes the shear stress as a function of the derivative of the velocity. And this now holds everywhere within a Newtonian fluid. So if we consider that we have, let's say we're looking at the flow between, I have my two hands moving, right, across one another, or I'm really zoomed in on a bearing, right? We can imagine that the fluid inside is composed of many of these little tiny differential elements stacked up on each other. And each one of them is feeling a shear stress, right? Each one of those little fluid elements, little tiny differential fluid elements, is feeling a shear stress. And so within each one of them, the shear stress is mu times the derivative of velocity of one of those little tiny fluid elements, right? And that means that, like, if I'm considering this flow between my hands, the little fluid element that's in the middle, right? It's not at the surface of the fluid, but it's still experiencing a shear stress. Does that make sense? So this holds everywhere within the fluid, as well as at the edges. Yeah, it's a good question. Yes. Yeah, we just set it up to be 0 to simplify the math in this expression. But we could have said U here was, something, big U. Top U was big U plus delta U, and we actually end up with the same expression. Yeah. Another way of thinking of it is that we did this derivation in a frame of reference, moving with the fluid element. So if we considered that we're sitting here, so if this fluid element is between my hands as they're moving this way, we're sitting at this one in the middle that's kind of moving at some velocity. If we're like moving at that same velocity as we do this derivation, we hit the wall eventually, I guess. But if we're moving at the same velocity, then U in that frame of reference would be 0 at the bottom. Yeah. Okay. What else? Okay. I clearly need to streamline this explanation. Okay. But in the end, we have this linear relationship that we use as the definition of a Newtonian. So if we consider flow between flat plates, right, as I've been illustrating with my hand, we can use this definition of a Newtonian fluid to determine what the velocity profile is for this flow between flat plates. So if we want to set up this problem, we need boundary conditions. Our boundary conditions are going to be that the velocity is 0 at the bottom. So we're going to imagine we have a fixed bottom plate. And we have a top plate moving at some velocity equal to V, big V. And we have some viscous fluid in between the two flat plates. And now the question is, and the answer is already given here, but the question is, what is U, right? What is the velocity within the fluid as a function of Y, function of the distance away from the fixed plate at the bottom? So we are going to impose what's called the no slip condition, which says that at the boundary of where the fluid meets the solid, we're going to say that the fluid velocity is equal to the solid velocity at these boundaries. And that's a little weird, right? So we're saying that at Y is equal to 0, what's the fluid velocity here? 0, right? Meaning that the fluid is not slipping, or the fluid that's right in contact with the wall is not slipping or sliding against the wall. It's at exactly a velocity of 0. And up here, right, the plate is moving at velocity v, and so therefore we're going to say that the fluid at the top is also moving at velocity v, slipping or sliding. It's also moving at the velocity v. So that's our no slip condition. We'll be applying the no slip condition frequently when analyzing flows in fluid mechanics. It seems like it must not be true, right? It feels like the fluid has to be moving near the wall. But in experiments to measure whether or not there is actually slip, they almost always find, and I'll tell you the exceptions, they almost always find that the no slip condition holds. The exception are things like, if you consider a really hydrophobic surface like a carbon nanotube, a really hydrophobic surface like a sheet of carbon. If you roll it up into something like a carbon nanotube, where you have an aperture that's about the same size as a water molecule, then you can get those water molecules to actually slip through that carbon nanotube. But you have to go to kind of exotic materials and size length scales in order for there to be any observable fluid slip. So this is a good assumption in general. Yeah. Is water still considered a fluid when it's flowing one molecule at a time? Well, yeah, that's a good question. So what assumption would be, what's that? Yep. So what assumption is violated for flow through a carbon nanotube? The distance between molecules is comparable to the length scale that you care about. So the continuity assumption is violated for flow through a carbon nanotube. It's still a fluid. The equations that we've derived would not hold. So, for example, the expression that we derived here, tau is mu du dy. This is meaningless when you have fluid that's not a continuum. Yeah. Okay. Yeah, go ahead.
Just real quick. So if the part at the bottom is moving at 0 velocity, how much like the bottom molecule is moving at 0 velocity? The bottom sitting here, and how much is the bottom?
Yeah, I mean, mathematically, we're saying that the velocity goes to 0 as y goes to 0, basically. So if we plug in, y is equal to, 1 nanometer away from the surface, right, from our final velocity profile, we'll see that there's a velocity that's non-zero there. But you're asking a question that, like, is at this boundary of the continuum assumption and and non-continuum physics, right? So yeah, I just say that's a good question. Yeah. Yeah. And to address that would require, we could do something like what's called molecular dynamics simulations, where we actually simulate all of the materials as individual molecules. And then you get into things like what's the roughness of the surface on a molecular level and all kinds of other things. Okay. All right. So by a force balance, so if we consider this plate moving at a constant velocity, the force that we're applying, or the shear stress that we're applying to the fluid, has to be constant as well. Otherwise, we'd have an acceleration. Otherwise, it would have to be accelerating, right? So if we just did a force balance on this moving upper plate to try to figure out what force I'm applying, it has to be balanced out. Whatever force we're applying has to be exactly balanced out by the drag that the plate is experiencing. Otherwise, there would be an acceleration, and we wouldn't have a constant velocity. And so since this tau is a constant, we can use our expression, our definition of a Newtonian fluid. We assume there's a Newtonian fluid in the middle, and write du dy is equal to tau over mu. Tau, constant, right, by that force balance argument. Mu is a constant defining how the fluid, what the fluid viscosity is. And so this whole thing is equal to a constant. Yes. It's a Newtonian fluid in the middle. Yeah, this should say Newtonian instead of viscous fluid. And we can integrate this, use A plus BY. And then we apply our boundary conditions. And so we say at we know U is equal to 0 at Y is equal to 0, right? So if U is 0 and that term BY is 0, therefore A is 0. U is equal to V when Y to H, and so we can solve for B. And therefore we derive the resulting velocity profile. U is V times Y over H, which is the linear velocity profile that was shown here already. Okay. And we are out of time. We can use it then to derive the applied shear stress, but this is where we're going to pick up on Friday after viewing a few videos about viscosity within fluids. Okay. H is height. H is the distance between the plates. That's correct. All right. Thank you all, and see you on Friday.